Hello and welcome to this session on Geographic Calculator 2015. I'm Katrina Schweikert, an application specialist, and I'm here with Sam Knight.
Okay, hello everyone. Today's session is going to be working with custom definitions. We're going to be working through a scenario that actually came to us from a customer on implementing a custom projection that required more than the usual custom coordinate systems. So we're going to step all the way through creation of a fully custom coordinate system and then verifying that same system. So let's get started here in the Geographic Calculator. Now what we're going to be doing is implementing a custom coordinate system, but where exactly did this come from?
So this request for a custom coordinate system came into our tech support team. They were looking at data in Minnesota, and it was using a custom coordinate system that was not part of our normal system. It uses a completely custom ellipsoid and datum.
Okay, so that's a bit of a special case. So first it took a little bit of research why there was this one system that was missing. And what that led us to was an informational website, and what we're looking at here is the DOT website for the state of Minnesota. And the county that was requested was called St. Louis County Transverse Mercator Coordinate System of 96. It seemed like something that would normally fall into the regular scheme of county-based coordinate systems they have for St. Louis County, but it was designed to cover the entire county, which if we were to look through the table of all these other coordinate systems, we would see that they actually have three coordinate systems. So their normal low distortion projection system covers three different strips of the county, and then they also added on this extra coordinate system that covered the entire area. So what we're looking at here is this little note section down at the bottom, and we see that there are parameters there. We have a whole bunch of stuff mixed together. And this is where things get a little bit interesting on this system and what makes it such a good example. We see that we've got some projection parameters, and we've also got some ellipsoid parameters in there. We see semi-major axis and semi-minor axis, which normally wouldn't be anything surprising, but in this case turns out to be not similar to GRS 80, which would be the ellipsoid found inside NAD 83. So this took a little bit of extra doing, and what we're going to be doing is stepping all the way through defining this completely new system into the Geographic Calculator.
So which of these parameters do we need to pay attention to?
Okay, so to split these up, I mentioned we had a couple of different things in here. So we see some terms like central meridian, latitude of grid origin, false northing, false easting down there, and then semi-major and semi-minor axis, scale factor, inverse flattening. This is kind of a little bit mixed up, and it looks like these were sort of partially added in the order that they'd be put into some software and partially not. So specifically, we need to break these things down into their components. And so what I'm going to do is just pop open a little notepad window that I've done to separate these things out, and we'll put them side by side here. So specifically, the ellipsoid parameters on this are the ones semi-major axis, semi-minor axis, and the inverse flattening. We only need two of those. We need either the semi-major and semi-minor, or the semi-major and the inverse flattening, but it is nice to have them all there just as a quick check. The rest of the settings that we have there are actually projection information. So central meridian, latitude of grid origin, those are where the projection is going to be centered, and then false easting and false northing, how we manipulate those coordinates to put the numbers into the ranges that we want to be working with up in that positive quadrant, and then the grid scale factor. And particularly of note here, the ellipsoid parameters I mentioned are not the same as GRS 80, and the scale factor is not what we very commonly see on a lot of transverse Mercator systems, either 9999 or 9996. This is what's called a low distortion projection, And it's basically you could describe it as a hyperlocal projection designed to suit very closely the ground in the area of this working area, which is St. Louis County, Minnesota. Below that, we have a control point that we got from a survey sheet that we'll get to a little bit later on when we actually check this thing out.
Okay, so let's move into the calculator application. And we've got a lot of parameters to look at, so where do we start?
Okay, so there's a bit of a hierarchy here, and it's a little bit like that old song about the leg bones connected to the knee bone and the knee bones connected to the shin bone. We're going to start with the ellipsoid. That is the most granular piece of a coordinate system. Since we need a custom ellipsoid for this case, that's what we actually have to start with. We're going to have to create a custom geodetic datum out of that ellipsoid, and then we can move up to the full-on coordinate system part of it. So we have to go in order, and if we needed to start with something even more specialized, like a custom linear unit to define that ellipsoid, we'd have to start with that. But so for this case, we're going to start with a custom ellipsoid, and we're going to be doing most of our work up here under the data source menu. So we're going to start in ellipsoid definitions. And here you'll see a list of all of the normal out-of-the-box ellipsoids. What we're going to do is click the addition button right beneath that, and it's going to open up a new panel to define a completely new ellipsoid. And so I'm just going to give this a name of St. Louis County. And I'm going to call that 96 because that's the date that keeps being added on here. We could as well also fill out some remarks, and if you're going to be working with a custom coordinate system that you're getting from a particular place, it's usually a good idea to toss that in there. What I might do in my own remarks here would be to take the web address of that DOT webpage we were just looking at, maybe paste that in there, just so we have a good way to get back to where those things came from if we get down the line and discover there might be a problem with anything we've done. So the identification is there. We're going to click over to the definition tab, and here's where we put in our parameters. So we have, again, a couple of ways we can put in the ellipsoid parameters. We have all three of them, and we only need two of them to fully define that. Semi-major and semi-minor is probably the simplest, but then at the bottom we also have an option for the inverse flattening. And for those of you not familiar with what flattening is, it's a simple ratio that is used to describe the relationship of the semi-major, the bigger axis of the equatorial plane, the relationship of that proportionally to the semi-minor axis, which is the radius from the equator, from the equatorial plane to the North Pole or the South Pole. So only two of those three parameters are needed, and we have all three, so we get to take our pick. I've got this handy dandy little cheat sheet with all my parameters copied right off of it. So what I'm going to do is take my semi-major and semi-minor, and I am simply going to copy and paste those right into our interface. So I'm going to start with the semi-major axis, and I'm going to get rid of all the little placeholder commas that are in there. And semi-minor axis. And while I'm doing this, we can just talk a little bit about where those come from. In a low distortion projection, there are a few ways that we can get that low distortion quality. And what we see with this artificial ellipsoid is actually a kind of an older way of doing this. In the current best practices on a lot of low distortion projections are to not change the ellipsoid. You keep it on the standard ellipsoid for the area, but they actually mess around with the grid scale. And they accommodate it with using very strange grid scales, but it doesn't require any custom ellipsoids. And we'll come back to that in just a little bit, why exactly not having a custom ellipsoid can make things easier to work with. So I pasted in my semi-major and semi-minor, and I clicked OK, so I'm back out to the main ellipsoid list. And we'll see that that new entry is just going to pop right in the list there. There's going to be no padlock icon indicating that it's in our custom data source, and we can do anything we want to it. We can edit the parameters, change its name, and so on. We'll also notice that we have the semi-major and semi-minor that we pasted in, and it calculates for us what that inverse flattening ratio is. And we can also compare that against our parameters and see that that matches way far out there after the decimal place. So we're good with that. At this point, I'm going to hit save, and it's going to say, would you like to put this in your custom XML? And I'm just going to say yes. We're going to be doing a whole bunch of that as we add these new systems into the database. So I'm going to click OK, and there's our ellipsoid.
Okay, so now that we have an ellipsoid, what's next?
Okay, so the ellipsoid is going to be connected to the datum. And so we have the size and shape of the planet that we're modeling, and now we're going to take a look at adding in the datum, which basically takes that ellipsoid and it's going to pin a reference meridian on it. This is a piece of information that is actually missing from our defining page here. It does not specify specifically what this is based on, but from experience we know that this is going to be in the US. This is deriving from an inflated version of NAD83, and so we can extrapolate from that this is going to be using the Greenwich prime meridian. That's where sometimes we get a little bit tricky when we have these custom systems. You may not actually have the full information for defining it, and we may need to do a little extra research, as we did in this case. So what we're doing now is adding a horizontal datum. So you'll see again our whole list of datums. There are somewhere around 500 of these predefined. And normally for a system in the United States, it would probably be based on the NAD83 datum. The surface that we're working with actually does derive from that. It's just inflated. It's not the same size. It's just a little bit bigger to bring the geoidal surface close to the projection surface in this case. So this is going to be the same process. We're just going to add a new object into the database. We're going to give that a name, and I'm going to call that the same thing. I'm going to call this the St. Louis County datum, and let's go ahead and call that 96 because that's the year. And the parameters for this are actually fairly simple. So we've already defined the ellipsoid, and now we just need to say that that ellipsoid is the one that is used inside our datum. So there we go. There's the ellipsoid we just defined. I'm going to go ahead and say OK. There it is. And next up, the prime meridian, the other piece we need. And there's not many to choose from, and we're going to go with the Greenwich World Standard and come back to our definition. So for the datum, that's pretty much it. We could go into the identification. Again, we could put in things like the URL to that web page where we got all our information from. However much information you want to put in there, we're going to say OK. And then we'll see our new datum showing up down in the list of all of our datums. And again, we're going to go ahead and save that into our custom database and then move back out into the application.
Okay, so we define the custom datum. So now we need a projection.
The projection's one more step away. First, we need to actually put that into a geodetic coordinate system. So the projection is a projection of a geodetic coordinate system, and the geodetic coordinate system gets all of its size and shape from the datum. So the datum is going to go into the geodetic coordinate system. We're getting into a little bit of word soup here. We're going to go back up to our data source menu, go down to coordinate system definitions, and we're actually going to do both of those things right in this dialog. First, we're going to work under the geodetic category to add that custom system, and then we're going to place that into the projected system with all of the projection parameters. So to properly place this, we saw the ellipsoid menu and the datum menu. Both of those pretty much just have everything in one big folder. Under the coordinate systems, we organize those a little bit more cleanly. And so what I'm going to do here is I'm actually going to place these down in the folders where we would put them if we were modifying our data source here, just to keep things organized. Some folks put their custom systems right at the very top level. You can actually create your own systems anywhere throughout here. Some folks like to put their custom systems right at the top. Some folks like to add in their own custom folders to keep things sequestered from others. What I'm going to do is use our own standard around here, and I'm going to add this down under the smallest political subunit that we put in there where it makes sense. So I'm going to go down under the United States, and I'm actually going to add in a folder here for Minnesota. Okay, so I've got my folder, and now in that new folder, I'm going to go ahead and add a geodetic coordinate system. So I'm going to call this one more time, St. Louis County Coordinate System 96. And again, the remarks, all that same source info would be great in there if we wanted to take the time to do that. So under the definition, a geodetic coordinate system is really very simple as well. It's only got two really defining parameters and an area of use. Now the area of use is not really a defining parameter, but it is a helper. So we can apply automatic filtering of that coordinate system depending on the data that we're feeding into the interface. The default on that is world, and so in this case it would probably make sense to tighten that down a little bit. So what I'm going to do is do a quick search for Minnesota and see if we have any predefined areas of use for Minnesota. And you'll see we have a few in there. So some areas of use for the state plane coordinate systems. And I'm just going to take the general one for all of Minnesota. If I really wanted to be a stickler on this, I might actually go ahead and add a custom area of use bounding that tightly around St. Louis County. I'm not going to take the time to do that right now, but that's just as simple as adding a minimum bounding rectangle around the working area for that system. And then the defining parameters. So this is actually fairly simple as well. We have a point style, and the point style is essentially the units. It's just a little bit more than the units. It's in this case of a geodetic system, we're talking about latitudes and longitudes. So we're going to be working with a geodetic point in degrees, and the nuts and bolts behind that are it actually has the coordinate axes and things like that, which direction positive is. So it implies a few more things than just the units, but effectively it's essentially just units. So we're talking about degrees here to base that on. You'll see a whole lot of other sort of more academic, technical standard names for very similar ideas. Some of those alternate units, things like grads, and then some of the academic definitions that we might see in the EPSG. Really all we need are geodetic points in degrees, and there we go. And then lastly, the datum. And here we're just simply going to select the custom datum that we made in our last bit of that exercise. So I'm going to scroll down. Accidentally scrolled sideways there. I'm going to scroll down to St. Louis a little farther, and there is our custom datum. So we're going to go ahead and double click to select that, and there is our latitude longitude geodetic coordinate system definition. So we're going to go ahead and say OK, and there it is in my Minnesota folder that I've placed down under the US, North America, and the geodetic category. So again, I could place that anywhere in this directory structure that I see fit. I like to keep stuff fairly tightly organized in there. So the next step is finally the projection. So we're going to go down under our projected category, and I'm actually going to do the same thing here. I'm going to go down under United States, and we actually already have a Minnesota folder in there. And this is where we have all of those other county coordinate systems. But we don't have the specific full county zone. You'll see we have the North Shore, the Central County, North County, and South County in there. So there's a few different versions of coordinate systems, but none of them, other than this new one we're adding, actually covers the entire region. So this one's kept separately because it's not quite as granular as some of those others. But we're just going to add this in here. And so we're going to go ahead and say new object in there. And this is going to be almost our last new thing. So for the name, again, St. Louis County, and this one actually has an official name that is listed in there, so we're going to go ahead and call this one by its full name, which is St. Louis County Transverse Mercator 96, or SLCTM 96 for short. The definition, this is really our most complicated piece of the puzzle here. Again, we have the same area of use to pick out, and I'm just going to grab onto our Minnesota one that we used in the last step, that first general area of use for all of Minnesota. Again, it's a little baggy, but we can take care of that later if we wish.
So that area of use is what's going to come up when you use the map search, is that right?
That's right. So if you feed some data in there, it will limit that particular coordinate system to only if you're loading data within that region. So if you have the coordinate system filtering turned on. So if you were to say, I'm working in Maine, where we happen to be, and you load data in with that, it will exclude this coordinate system from being a possibility. And again, the default on those is world, and a lot of folks that are just working quickly through there leave that set to world. And as long as you're comfortable with seeing that a little bit more often, it doesn't really hurt anything, because it's not really a defining parameter. It's just there to help you as the end user filter out your list and just not see more stuff than you need to see when you're loading in various pieces of data. So again, like the geodetic coordinate system, we need to pick a point style. And so for this, this system is fully defined in meters, but interestingly enough, all the points we've seen in it are in US feet. So what I'm going to do here is I'm going to say that the coordinate system actually uses US survey feet as its default unit, but then I can go ahead and define this in meters. So we really can customize a lot of these parameters. Down under Geodetic, that is where we're going to grab on to the new geodetic coordinate system we just made in that last step. So that's just simply selecting our geodetic system. The default projection comes up is transverse Mercator, and the reason for that is this is the most common coordinate system projection used anywhere on the planet. The vast majority of modern coordinate systems are transverse Mercator systems. And so we have that come up by default there. So in this case, we can just leave it. If we were doing something else, you'd simply hit the drop down and find the particular projection that you need. So we actually do need the transverse Mercator one, so we're good to go there. And now the rest of those parameters, so longitude of natural origin, false easting, false northing, all those defining parameters for the projection, we need to get those off of our little cheat sheet of parameters that we have over here. So we have central meridian and latitude of grid origin, and we see some different terms here. There are a lot of different words that mean the same thing when it comes to these parameters. So for this exercise, central meridian is actually the same thing as longitude of natural origin. So we're going to take our 92 degrees west, and we're going to paste that right in over there next to longitude of natural origin. And because it is 92 degrees west, I'm going to hit minus on my entry there, so it puts us in the right hemisphere. Then false easting and false northing. Those are actually fairly standard terms. We'll see those most of the time in there. We have a false northing of 1 million meters and a false northing, false easting of 1,450,000 meters. So let's go ahead and we'll just copy and paste those as well. False northing is 1 million, and I'm going to go ahead and get rid of those little commas in there. And 1,400,050 for our false easting. And again, get rid of our little commas. And then latitude of natural origin. That's another one, has a slightly different term in here. We have latitude of grid origin. That is effectively the same thing. So we're going to copy that one out and paste that into our origin. That's in the northern hemisphere, so we're going to leave that positive. And then lastly, we need our scale factor. And the scale factor here, for anybody that is familiar with transverse Mercator coordinate systems, you'll note that's not an entirely normal looking scale factor. It goes much farther, and that is really how we get these low distortion projections tight to the ground, is by manipulating that scale factor value in all of those parameters. So we've entered all of those in there. As a last step, because there are a lot of numbers here that we're looking at, I usually make a point of double checking that I've pasted everything in the right place. So central meridian is longitude of natural origin, 92.45 degrees west, 1,450,000 false easting. The units are meters. We could click that meters button right there and change that to something else if we needed to. Match up the false northing, match up that grid origin latitude, and our scale factor, just to double check that we've gotten all the parameters right out to the very end. We need every single digit in there that we've got. And so it looks like I haven't made any mistakes here. Got lucky this time. So if our system is fully defined, let's just double check that we entered in a good name, and it looks like we're okay here. So I'm going to go ahead and hit OK. All right, and there is our new projection down in the list.
Okay, so we created a lot of custom systems there, so let's just review a little bit. So we started with the custom ellipsoid, and then we created the datum, and then the geodetic coordinate system, and then lastly the projected coordinate system.
Right.
So are we ready to use this coordinate system yet?
Nope, there's one more piece we need to do. And so again, I'm going to go ahead and save our data source changes that we've done so far. And I'm going to close out of there. And the last piece we need to put in for this is a transformation. And this last piece here is actually one of the reasons this type of local low distortion projection stopped getting implemented quite this way a few years back. And the reason for that is implementing a lot of different custom ellipsoids and custom datums and custom transformations to support all of those put a lot of overhead into coordinate transformation libraries. And it is a necessary piece. We can't avoid it if we want to relate this to a basically this system to any other system. And most likely for the area of the world this particular system falls into, we would want to relate that to NAD83. And NAD83 is actually the sort of ultimate base system that this particular set of datums came from. So the ellipsoid parameters are simply inflated from the GRS80 ellipsoid parameters. And it basically puts the surface of that ellipsoid a little bit closer to the actual surface, the ground itself in those areas. So very, very custom systems here. They are all ultimately based on NAD83. Along with all those parameters that we got, defining the projection and the datum and the ellipsoid, along with that, what we really need is a set of coordinate transformation parameters. And this is something that has sort of fallen off over the years on some of these older style low distortion zones, is that they actually don't have a transformation. You essentially do what we call a zero shift from the county model to whatever it's based on, and in this case that is NAD83. So what we need to do is set up a coordinate transformation from the new St. Louis County datum that we had, transforming that to NAD83. And the shift that we have to put in there is nothing. It's 0. And what that allows us to do is connect the dots between the St. Louis County system that's going to be on one side and NAD83 that's going to be on the other side. But it allows us to basically enter the transformation part and leave one datum and move over to another. And really a zero shift, what that means is we're saying that they're centered on the same place, but they're different sizes. And so it allows us to mathematically move from one model to the other just without actually moving the center of those two models. So that's going to be our last step before we can actually implement our test point here. So again, one more time, we're going up to the data source menu under coordinate transformation definitions. And in here, we've got two categories. We have single transformations and concatenated transformations. We're implementing a single transformation that is a type of datum. So we're basically doing a datum shift here is what we call these more colloquially. Again, I'm going to go down under my, my local folder. I think I glossed over the concatenated transformations. Concatenated transformations are combinations. Those are two transformations glued together. And so first, if we were going to make one of these, we would need to make a single transformation first, and then we could call up multiples of those into a group of them as a concatenated shift. So what we're doing is a single datum shift, and we're going to place that down under North America, United States, and in this folder, again, I could add that Minnesota folder below it, or I could just add it right into the main United States folder. And that's what I'm going to do here, just to save a couple of clicks for myself. And I'm going to add in, I'm just going to abbreviate this. I'm going to put in SLC 96, because that's what we had for the name of that datum, St. Louis County 96 to NAD 83. And that's a very common style of name for a datum shift, the input system to the target system. And again, you are free to put in whatever name you've got in there. I'm just going to follow our own standards. Again, area of the use. This really helps limit things down for the transformation selector. So again, I'm going to grab onto our Minnesota area of use. Looks like I need to spell it right. Minnesota. There we go. And grab onto that first one. This is really the place above all others where it would make more sense to apply a tighter area of use, or to go ahead and take that extra step and put in a custom area of use. Because this is so local, and there's only going to be the one transformation to it, that's not really going to be that much of an issue for most people here. And then the source and the target. So in this case, because we are implementing a zero shift, it actually doesn't matter which of these goes first. If we were doing anything that had a direction where we had a positive or negative X, Y, or Z shift in these, then it would get much more important. For this case, it is not quite as important. But typically, the way these are most commonly written down, and I'm making a generalization here, is the more local version of the datum goes first, and the larger, more global datum is typically the target. That is not a hard and fast rule. That's just something that's a little bit common. So for my source, I'm going to go ahead and grab onto our new St. Louis County system. And for my target, I'm going to grab onto NAD 83, the full North American datum. Now the method doesn't particularly matter. This one gets a little tricky. The default method is a geocentric translation. That is a simple 3-parameter shift as another name for that. That is a very common method to leave when doing a zero shift. We're effectively going to be doing nothing mathematically here other than moving from one size ellipsoid to the other. But most commonly, when executing a zero shift from one to the other, you will very typically see those implemented as a 0, 0, 0, 3-parameter translation, just to keep things simple. Mathematically, it would be just as correct to do a 7-parameter or a 10-parameter shift, but there's really not much point in changing that to something else here. So we're going to do a shift from one to the other of 0, 0, 0. They're in the same place, they're just different sizes. That's really the only thing that is going to happen on this. The identification, again, we don't need to put in much there. We could put in any source information that we have on these, and we're going to say OK one last time. So there's our new datum shift, applying the shift between our custom datum and our more standard survey datum. So I'm going to save those data source changes one more time. They're all in my custom XML now. And we're going to say OK, come all the way back to our main screen. Now, testing this out is really critical. We have our input coordinates. I've actually already pasted in some input coordinates. We're going to take a super quick look at where we got these particular checkpoints, but it is very critical when implementing any custom set of parameters to have a checkpoint that's a known good control value to compare that against, just to make sure everything in there is properly done. When I was practicing through on some of this data, I found that I made a simple typo in my ellipsoid parameters, and that actually messed up the conversion that I got on the output. So it's very, very critical to always just double check all those parameters along the way, and then once they're finally implemented, a known good checkpoint. And so what we have here is I'm going to open up my browser again, and I'm going to hop over to this PDF that we got, and this is basically just a public survey record that came out of Minnesota in this particular coordinate system. So you'll see it's a very typical survey sheet. It shows tie-in to the local network, shows the benchmarks. In this case, it's a bunch of trees that are referenced to tying a pin down on this trail. And down in the lower right-hand corner here, we have a series of coordinates. So we have nat 83 latitude and longitude in degrees, minutes, seconds. We have the SLC-TM 96 transverse Mercator values, and those are all going to be in feet. And then we have a nat 83 state plane value as well. So 3 different coordinate systems representing the same point. And this gives us a very good checkpoint. We can also check these against things like USGS benchmarks if we've got control data across multiple other survey systems. But typically these are going to come from some type of survey control. So this one just happens to be a public record in the area of that coordinate system that actually uses these. So we're going to take these values, and I've already got the latitudes and longitudes punched in over here on the calculator. And so what we're going to do is finish setting this up. So to do that, what we need to do is change our output coordinate system and select our new St. Louis County coordinates. So down under projected, North America, United States, Minnesota. We'll find our new custom coordinate system. So there we have our system, and now to link these two we need to select the transformation to get from nat 83 to the St. Louis County horizontal data, again with that 0 shift. So we double click, and there is our one available transformation for our brand new custom system. So to complete this check, where we got this value from was that survey sheet that we talked about a little bit ago. We have a nat 83 latitude longitude value. We have a St. Louis County transverse Mercator northing and easting. And additionally, if we wanted to go all the way with this, we could even check this against another projection, the state plane coordinates for this particular location. So in the calculator, we've punched in our values, and we need to just simply go ahead and finish off the calculation. And we get our calculated output on screen, and we can compare that directly against the sheet that we have here. And it looks like we've done something wrong. So this is a great example of why it is so important to actually finish off these checkpoints. You might have done something like a simple 1-digit transcription error somewhere in one of those parameters. And in this case, it looks like I think we actually made a quick little typo on our checkpoint itself. So it looks like the coordinate, we accidentally put in 96 instead of 93, and that last digit there I believe should be a 4 from that sheet. So making sure our coordinate value is exactly as we expect it to be. Let's go ahead and try that calculation again. And when we compare, we've got, let's see here, 3,699,774.71 and 4,601,617.214. Looks like we have 2 places of precision out here. If we wanted to chase that last little 4, let's go ahead and bump our grid coordinate precision out there all the way and calculate that off, and there we go. So we are matching this down to the looks like fractions of a millimeter level. So once we got our checkpoint correct in there, everything is working just fine. So the process, again, overall, just to recap that all, we started off with our custom ellipsoid. We entered in a custom datum based on that ellipsoid. We entered in a geodetic coordinate system based on the data. Then we turned that into a projected coordinate system. With the transformation, as the last piece we defined, then we go ahead and do that checkpoint. So this is a great example of a fully custom coordinate system. This particular one, we were actually adding into the calculator the 2016 version that we're working on for the winter release. So we just stepped through this exercise ourselves here, and this system will actually be permanently in our database. But there are still other systems out there that you may need to add as a one-off system yourself. There are some next things that we can do with these once they're permanently in place, but that is the overall process of actually defining one of these things.
So Sam, that was quite a few steps to create that custom system and check it. So what if we want to share this now with other people?
Right. Okay. So we've got a fully custom coordinate system, and if we're not working by ourselves, if we're not just a one-off operator using the calculator, we might need to give this to somebody else, or we might need to take it to some other software system. There are a few different ways to do that, and they go right hand in hand with all the typical ways we share workspaces or definitions with other users in the calculator. So first, underneath the File menu, if we simply want to pack up our whole workspace and share that with another user, there is an Export Workspace option right there. What that will do is actually pack up the workspace. It would pack up this new test job that we had created as well, and our custom definitions, and put that all in a zip file that we could give to another user of the Geographic calculator, and they could import that whole workspace containing the view file, the extra systems, and such. As well, in this case, that would actually carry out with the checkpoint. That would be essentially sharing everything with somebody else. But say, for example, that you don't want to share the whole workspace. If you and your colleague have your own calculator installations, your own workspaces that you're happy working within, under the Data Source menu, there are some options for exporting objects as well here. So we can choose to export objects to XML, and that is our own XML format that matches the structure of the custom XML itself. But this allows us to simply pick out individual definitions from that database and put into a little mini snippet of the database that you can send off to another user. Once you send that to them, they use the option to import those objects from the XML, and then they show up instantly in their database. Now the process for this is working through some familiar dialogues here. These are very much like the selection dialogues, except in this case we see all of the different geodetic components grouped in one place here. So because we have a fully custom system here, all the way down to the ellipsoid, we need to build up the pieces that we're actually going to share with another user. So we would open up our ellipsoids, find our custom ellipsoid there for St. Louis County, say OK. We'll see that gets added to the list up there, tells you what type it is, what its name is, and then the GC code, the internal identifier for that particular entity. Then we could grab onto our horizontal datum that we had created, just like the ellipsoid. Ooh, mouse jumped over on me there. Just like the ellipsoid, we find our St. Louis County horizontal datum. That gets added to the list, and so on down the line. I'm not going to step that all the way through, but we would next go grab the geodetic coordinate system, the projected coordinate system, and as well the transformation. We could grab any other systems too. It doesn't have to be just one specific group. If we had other custom systems and we wanted to cherry pick which ones to share with another user, we could build a list here of any number of those geodetic objects. And again, those all, once we click OK on this, that will prompt us to save these out as an exported objects file. That is a Blue Marble internal format, and it is simply the XML structure that we have for the main database itself. Then your colleague will take that file, go to their data source menu, and import objects from that XSP file that you're going to give them. That brings in all of those objects, all of those entities, and allows you to make those portable. One more way to get those out of there quickly is if you have something simple like just a projection. We can right-click. Once we have that projection defined anywhere, we can right-click on that, and you'll see there's an option to export directly to file on a single coordinate system. And what this allows us to do is write that out either as an Esri-compatible PRJ file, a well-known text file, that's a WKT extension, very, very similar to a PRJ file in structure, or a GML file, coordinate system definition. Each of those will write out a single file containing just the coordinate system definition that you have, and they also do actually contain the smaller pieces. They contain the horizontal datum and the ellipsoid parameters inside there as well. The one piece that they don't carry over, those formats don't easily support, is the transformation, the zero transformation to another system. You just need to be aware of that when moving around the projections. But those are the main ways that we can share those out with another user.
So thanks for joining us. That's going to do it for today's session. If you have any questions, you can reach us at geohelp@bluemarblegeo.com. Also remember that you can subscribe to our YouTube channel if you're interested in getting notified about other videos. So thanks, Sam.
Thank you, Katrina.
Thanks for joining us. We'll see you next time.